Okay, there you go.
All right, thank you. So I want to talk about some work we're doing in California, working with the state of California and NASA to try and improve forecasting of snow runoff in the spring during the drought that they've been having. And this is probably the most exciting thing that I've gotten to work on in my career, and I'm really pleased to be able to share it with you. How do you make it go forward?
Right.
Okay,
Right.
gotcha.
Yeah.
Okay, so what I want to talk about is why we undertook this and how we got involved with the group at JPL, and then some of the preliminary results that we've had working with them over the last 3 years. So this is what the California drought looked like. And this is for one large watershed in the Sierra Nevada. It's the Tuolumne Basin. And is there a pointer on this? Well, so how do you make the pointer work? That's the pointer. Got it. Okay. So we ran the simulations for 2013, 14, and 15, and this is what these traces are. This gray area here is the historical record in the Tuolumne Basin, and the mean value is right up here. Here's where the peak usually was, somewhere around the 1st of June. And so you can see that it's been a very dry period of time. Not only dry, but very, very warm. This is the 13, 14, and 15 here for the Tuolumne Basin. There was actually less runoff in 1977, but it was much colder in 1977, and so there was probably more snow in 77 than there was in 2015. The problem with the way forecasting has always been done is shown here. A colleague of mine, Jeff Dozier, did some analysis in California for the American River Basin, and he was able to show that it takes a long time to get the calibration up to figure out how to relate how much snow there is in the mountains to how much runoff there's going to be. The statistics have a hard time capturing the current climate conditions, especially if they're not stable. And so what this graph shows is that half the time the errors in the forecast are greater than 20%, and 1 out of 5 years they're greater than 40%. And so the need to improve the way we do forecasting in these snow-dominated mountains is really important. So what I want to do is show you now is this the project that we're working on with NASA. The science questions we had is could we replace the statistical snow model with a physics-based snow model and run that in a sense essentially in real time in an operational framework, so that we could use a model based on the physics to predict what was going on with the snow cover, not only in terms of the basin condition, but the spatial distribution of that condition across the basin. And then we wanted to know if we could integrate this with airborne remote sensing coming from NASA to improve the way the physics-based model characterized the snow cover in the mountains. So the model we're using is called IceNobel. It has a series of state variables here. The liquid water content, the snow cover temperature, the surface layer temperature, and the density and the depth. And then it has some forcing variables. It needs incoming radiation. Whoops, I didn't mean to do that. So what we're getting from NASA is an improved net radiation parameter because they're using a spectrometer in their overflights and an active measurement of the snow depth. So what NASA was going to do for us was fly LiDAR before the snow flew and get the ground surface at very high resolution, and then fly LiDAR over the watershed every week during the snow season. And so we could then take that information from NASA and update the snow model to do a better job of predicting how much water there was there. When the project started, 2010 actually had a fair amount of snow in the Sierra Nevada, and NASA was approached to do this particular project, and it took them 2011 to get it together, and by 2012 we were into a drought. And so all we've ever had is drought conditions, which is both good and bad. The bad side is that there's not much snow. The good side is that if we can deal with a drought like this, then we can deal with almost any condition, because if you make a 10 centimeter error in the snow depth and you've got 3 meters of snow on the ground, it's not that big of a deal. But if you've got 40 centimeters of snow on the ground and you make a 10 centimeter error, it's a huge error. So the fact that we were able to do this during a drought year is really quite important. So the Airborne Snow Observatory is NASA JPL's program. This is from the eastern side of the Sierra Nevada. This is where they put the plane and pilot it for everything in the Sierra Nevada. They're flying about 6 of the large watersheds in the Sierra Nevada right now. I'm only going to talk about one today. This is the plane. They have a new laser. It's a dual scanning laser, so you get more hits per square meter, and that allows them to fly faster and higher and get the same kind of resolution that you would get if you flew slower and that sort of thing. So if we couple their data with our snow model, this is the Tuolumne Basin. It's about 1,200 square kilometers. It's Yosemite in the middle of it. This is Tuolumne Meadows right up here. Yosemite Valley is actually down there. This is the Hetch Hetchy watershed. It provides water for the San Francisco Bay Area and generates power. We ran the snow model at a 50 meter resolution over this, and the approach we took was we would start the model up on October 1 and run the model forward to the first overflight, which is usually around, well, for the first 2 years it was around March 1st. In 15 it was actually February 15th or February 12th. But the ASO data comes at a 3 meter resolution, but we aggregate that up to 50 meters for the modeling. So these are the products, the standard core products. Snow albedo from the spectrometer. We simulate the density field. The LiDAR gives us the snow depth, and by multiplying those two things together, we get the snow water equivalent. So you're seeing something here. This is really a first. This is a measured volume of water stored in the snowpack over a very large mountain area. And this is, if you're a snow hydrologist, this is really cool. This was the holy grail, was being able to make an estimate using some combination of models and remote sensing of what the volume of water stored in that snow cover was. So the procedure was that JPL would provide us with the snow depth. We would then simulate the density up to that point and then give them back the snow water equivalent. So the model does a lot more than just provide the density, though. The model tells you what the cold content is, whether or not the snow is ready to melt or not ready to melt. It gives you the layer structure. It tells you what the sublimation might have been. It gives you the surface water input or the runoff out of the bottom of the snowpack. And so the discussions immediately came to perhaps what we needed to do was to couple the model and the ASO data to a hydrology model of some kind and provide the forecasting agencies in California with a direct output result that they can use to forecast their reservoirs. So this is just an example of the updating that we do. This is, we ran the model forward to February 7th. This is what we said was there in terms of the snow water equivalent. And this is, after we updated it, this is what was actually there. This is the updating. So the stars are every time there was an overpass. This part of the curve here is what we simulated before we had the update, and then at the first update we realized that there was more snow there than we thought, so we had made an adjustment, and then you follow it down, and what you can see is that by 4 or 5 updates we're pretty much right on with what's out there. So maybe you don't need to fly it every week, but it sure is nice to have all those data points. And I'll run this. Probably have to do that from here, huh? Okay. How do I start it? I don't know how to start it. How do you start the?
That's a good question. Sometimes it doesn't work. So
It did when we did it. There. Ah, gotcha.
there it is. Good catch.
Okay. All right. So this is snow water equivalent for 2015. And you'll see in the upper right-hand corner here, it'll tell you every time there's an update. And then well, I can't run the second movie for you, I guess. Anyway.
If you go back and your mouse down towards the bottom of your slide with your mouse, it'll
Okay.
show you so just take your mouse and there you go.
Oh, there it is. Okay. So this is the cold content. Oops. I don't know how to push it. Oh, it's the left mouse. Okay, so this is cold content. So when the cold content is in the red, that means the snow's melting. So with this drought year, the snow there'd be an event, but it was a really shallow deposition event, and it would melt almost instantly. So this is the first scientific meeting where I've showed any of this. And so what we want to do now is attach the snow model to a hydrology model and see if we can improve the way forecasting is done. And I'll take questions if you have any. I can't
How do
hear
you
it.
expand that? The question is how do you expand that to other watersheds?
So, okay, I'll talk about. I see where you're going, and this is what's really interesting to me. The cost is if you're going to do one basin. So when the first year when we just did the Tuolumne, it was about $500,000 a year for that year to fly the Tuolumne. But by the second and third year, they were flying about 8 basins in the Sierra Nevada, and the cost had dropped to about $100,000 a basin.
So at that point now it's 2.5 million.
No.
So $400,000 for 5 basins.
It was about $100,000 per basin, and there were 5 basins. It was about the same cost for 5 basins as it was for 1, because once they've got the plane up there, the cost goes way down. There's another factor in that this sounds really weird, but the main cost on flying the LiDAR were the turns. So there were 243 turns to fly the Tuolumne. and they have to slow down and turn and get back online. And that was the biggest part of the cost of doing it. So if they fly 4 or 5 basins in a row, they have the same number of turns but 5 basins, and so the time it takes them to do it goes way down. We're flying basins in Colorado, the Rio Grande, and the Uncompahgre, and they're flying a couple of basins in Wyoming. Where I'm hoping to get them to fly the Boise River Basin at least once or twice this year. So it's possible. Yes.
So I have a question then. You were talking about connecting it to the hydrology model, but one of the other presentations that we heard this morning, I believe just the first thing this morning, was something about ocean temperatures, like gauging the stuff of ocean temperatures. And since you're talking about Sierra Nevadas, right? You're talking about California. Have you thought about kind of correlating whatever's going on with the weather coming off of the ocean hydrology and the stuff that you're doing with the LiDAR, like ocean temperatures?
I haven't. The LiDAR wouldn't give you ocean temperatures.
Right.
It'd give you ocean height.
Give you height.
It's not. It's just measure. It's a ranger. So LiDAR stands for light ranging and detection, and it just tells you the distance. And it's very accurate. It'll give it to you within a couple of centimeters. The real cool thing about the LiDAR snow depths is that the main uncertainty when you're modeling snow in the mountains is the precipitation, because we don't have much precipitation that's measured. When you get one of these updates, that goes away. You don't need to know it anymore. Now you know where the snow is. You know where it's been deposited and all that sort of stuff. So it really solves a couple of the major problems that we have in modeling the snow in a very detailed way in the mountains.
Which I have a question about that one. Is did NASA, as they were doing these flights, also do ground truthing with snow course data? Because yeah, the LiDAR will tell you this is your snow water equivalent, but was it really the snow water equivalent? Have they done any correlation work on that?
We've done a little bit. The problem in the Sierra Nevada, if you're not familiar with California, pretty much the entire Sierra Nevada is a wilderness area, and so you can't move around in it very easily. But we were able to get out into Tuolumne Meadows and take cores and that sort of thing, and the uncertainty was within the uncertainty in the measurements. So if you're taking a core, it's plus or minus 5% is about as good as you can ever do, and I'm good at it. I do it a lot. And we were getting those kinds of things. Now, to be fair, that's in a flat area out in the open. Who knows what it'd be like up on the slopes, but you can't get up on the slopes.
Well, and then there's the issue once you get up to a slope, there's drifting and all sorts of stuff. So
Right.
yeah, at that point.
Right.
Other questions?
So just kind of a brainstorm question. I've heard a little bit about green LiDAR, which lets you do stream depths, and I'm wondering, once you got the plane up there, would that be useful to actually give you some hydrologic information about what kind of runoff is occurring? Because that would kind of go together with your snow melt information.
I've heard of the green LiDAR, and I know they use it to map channels, stream channels, but I don't know very much about it.
And then you would have to get the aerial extend to get your discharge of how much. So you may have a height of a river, but you still need a full.
You have to develop a rating curve.
You need to develop a rating curve. Yeah. Which is a lot easier when you're talking about a cross section versus a whole channel. But it's an interesting idea.
I think the bottom line is that this experiment has shown us that we can do remote sensing at very high resolution, and it gives us useful information that we don't otherwise have. Even if they turned the thing off right now, we've got 38 LiDAR overpasses over the last 3 years that it'll take us the next 5 years to completely analyze.
Other questions? Okay, thank Danny, and